Okay. Probably better up there. Is that bar with the participants in the way?
No, I mean, you can minimize it on the screen. That's what I did.
Okay. Okay. So the first thing we're going to talk about now are diodes. It's really the first, well, it's not exactly an active device, but it's part of active devices. It's mostly today, they're semiconductors. The initial vacuum tube was a diode, and it worked by heating up the cathode enough to energize a bunch of electrons to make like an electron cloud, and then you applied a positive potential on the plate, which would attract the electrons and flow in that direction, and only from cathode to plate. Semiconductor diodes work the same way. They only flow in conventional current from the anode to the cathode. Electrons are actually going the other way, but we're going to talk about conventional current flow, which was defined backwards way back when Benjamin Franklin did it. So we're stuck with it. And it's actually the way holes flow when we talk about semiconductors. The basic diode will conduct when there's a slightly positive voltage with respect to the cathode, and it depends on the material. In the case of germanium, and some diodes are still made with germanium because it only has a 0.3 volt forward, what we call forward bias or forward voltage drop. In other words, it takes 0.3 of a volt before that diode will conduct in the forward direction. It will not conduct in the reverse direction until you exceed its breakdown voltage, and then it won't conduct anymore either way. In the case of silicon, which most diodes are based on now, it's approximately 0.7 volts. Now, those are important because there's two test questions about that. What the voltage is for silicon, and one about varying voltages for diodes. Special case is light-emitting diodes, or one of the special cases. And they're packaged in a transparent plastic material so that you can see the light. And it turns out all diodes and all semiconductor junctions actually produce light when the electrons recombine over the junction, because they give up energy, and that energy has to do something. It either produces light, heat, or vibration.
Not always in the visible spectrum.
Not, you know, and I can't go into the physics because I don't understand it enough of why some produce more light of certain frequency, some produce heat, like in the case of resistor. The same effect is that you're having electrons recombine with atoms so that excess energy is going into heat in the resistor. And that's where the power thing that we talked about came from.
I can't remember. It's like in the radioactive. What's it called?
Radium,
Yeah, is that essentially the same thing?
different.
How it lights up? I can't remember the term, but it's like a scientific.
That is totally different.
Okay.
That's radiation.
Yeah. And we're not going to go into quantum physics, which is how semiconductors really, really work, because I don't understand it enough to explain it. So we're just going to do the simple explanation.
For me.
Any questions about diodes? In the semiconductor diode, we make it with a junction of a P-type material and an N-type material. And I'll explain those in a little bit. And we call that a P-N junction. And it forms this little depletion region where the electrons are recombining with the positive ions, which are atoms that have lost an electron. We call them holes. So you got a recombination happening in that zone, and that's where you start getting into quantum physics with energy levels and things. The basic schematic and how we represent a diode is this filled-in triangle, normally solid, doesn't have to be, with a bar representing the cathode. And it's also showing the direction of conventional current flow. It goes in the direction of that arrow. Physically, and this is not true in all cases, but most of the smaller diodes are going to have a stripe on the cathode end to represent the cathode. There's others, sometimes it'll have a kind of a pointed, like a bullet shape, representing the cathode end. But in the majority of cases, small signal diodes are going to have a black or white stripe, depending on the color of the diode. I think for germanium, it's actually maybe red, because they're clear
I
glass.
haven't seen it, not over the years.
Over on the left-hand side, we're showing how electrons are flowing in one direction and holes are flowing in the other when you have an applied voltage that's great enough to overcome that energy barrier in the junction, which is about 0.7 volts if it's silicon and 0.3 volts if it's germanium. Okay, we talked about P-type and N-type material and things being made out of silicon. Silicon itself is a crystalline structure, has 4 valence electrons, and it is essentially an insulator, even though it's classed as a semiconductor. To make semiconductor devices work, we have to make P-type or N-type material out of silicon or germanium. In this case, we're going to make a P-type material. So we have this silicon crystal, and you notice these 4 electrons, and they form these, what we call covalent bonds with other atoms. And that's what causes the structure of a crystal. Silicon is a crystalline type structure. And what we do is inject and there's different ways to do it, and it's not important how, an impurity atom. In this case, we're using boron. And boron only has 3 valence electrons. So when you add those into the silicon crystal, you wind up with these gaps, okay, or a hole, which makes it have essentially a positive charge. That's why I call it P-type material. To make an N-type, we add something like phosphorus, which has 5 valence electrons. So 5 and 4 don't add up either, and we wind up with, you know, like musical chairs, and you take a chair away, you got an extra electron there. So it becomes a negative charge. So when we put them together, we've got a positive charge material on one side of the junction and a negative on the other. And getting across that energy gap has to do with why it's 0.3 or 0.7 volts and all the physics stuff, but you just need to know N and P-type material makes the junction. And we do transistors the same way, except we use 3 pieces of material. We use an N, a P, and an N, or a P, an N, and a P. This was just a little graph. If we had a perfect diode and there was no junction, this yellow plot or gold plot is what it would do. And because there's a resistor in series, that determines the slope of this line, okay, where we got voltage on this axis and current on that axis. If you remember, Ohm's law said resistance is the slope of the line, the ratio of voltage to current. Because of the junction barrier, the diode doesn't conduct until it's around 0.7 volts. It actually starts breaking around 0.6, and different diodes will vary. That's why it's an approximation. So, what electrical component allows current to flow in only one direction? Imagine that. Now remember, resistors do what? Oppose current flow in both directions. Fuses stop current flow when you get to whatever the value is where the fuse melts. And the driven element is part of an antenna. So in like most cases, a lot of those answers are obviously wrong. What are the names for the electrodes in a diode?
C, Charlie.
Okay. They actually should say in a semiconductor diode because, well, still called anode and cathode too, isn't it?
Pretty much so, yeah.
Usually you call it a plate, but yeah, anode and cathode. So the plus minus answer are just voltage polarities, nothing to do with it. Source and drain, which we haven't got to, which comes up next, are two of the terminals for a field effect transistor. And gate and base are two terminals for a bipolar transistor. How is the cathode lead of a semiconductor diode often marked on the package?
Straight.
B, Bravo.
I've never seen one that said cathode. I've never seen one with the letter C, or I've never seen one with the letter K. Sometimes the shape will be different, but it'll have a stripe or a different shape.
The question is often marked, doesn't say always marked.
Right. And that's another thing. Carefully read the questions. Read them twice. Because some of the questions are subtle. Which is true about forward voltage drop in a diode? .3 in germanium, 0.7 in silicon. Actually, there's other types of diodes where there's different values that we won't talk about. So general and extra. Let's see, proportional to peak inverse voltage. They essentially have a constant voltage drop. The diode is defective. Oh, that's kind of weird. And
Shorted diodes are generally only shorted for a microsecond.
yeah, usually they become an open circuit, very high resistance. What causes a light emitting diode to emit light? You have to have the current flow of the free electrons to recombine and give off their energy to create light. Reverse current, they do not allow reverse current, or at least minimal amount. It's in the microamps. Capacity coupled RF signal and inductively coupled RF signals have absolutely nothing to do with LEDs. Which of the following is commonly used as a visual indicator? And I didn't talk about that, but it should be obvious.
Yeah, that would be, of course,
Mhm.
for years.
Right. You can turn them on and off, or you can vary the intensity. Field effect transistors, Zener diodes, bipolar transistors are all in packages where you can't see the light, but there actually is some light at the p-n junctions. It's just that LEDs are designed with material that enhances that effect, and they can control the color with the different materials. Okay, transistors. So we're going to add a third piece and turn a diode into a transistor. You could almost look at it as back-to-back diodes. We got two types, bipolar, where we use a current to control, an input current to control the current through the transistor. In other words, it becomes a current controlling device, and we can vary how much current it allows with an input current. The field effect transistor also controls current, but we do it by an input voltage. So it acts like a vacuum tube where we use a voltage to control the current flow. And that's the basic difference. Is one is voltage controlled, the other is current controlled. We use them as switches where we operate either in the fully on or fully off state, or we use it as an amplifier. We will have it set up to operate where it's essentially on halfway, if it was like a Class A amplifier. And then the input signal will cause it to go up to maximum current flow, maybe down to minimum current flow, which would be the maximum. Hello.
Sorry, that was my computer talking.
Oh, okay. I thought you had a question. Okay, when we're using it as an amplifier, we have gain, okay, which is the ability to amplify the input signal. And normally we talk about power gain, where the output power is greater than the input power because it's an active device. So we're actually supplying power. And we're actually going to supply more power than we get out of it. It will amplify the input signal, but you've got to supply power to the device itself. And there's no such thing as a free lunch. So you're not going to get 100% efficiency, which is the ratio of the output power to the input power. We also can talk about voltage gain. It can be set up as strictly a voltage amplifier as opposed to amplifying current, or just as a current amplifier. There's different configurations of whether it's a common emitter or a common collector or a common base. And the same thing true for field effects, different configurations, and they behave differently. So let's talk about a bipolar, which was the first produced, but field effects were actually discovered and they could never make a practical one until much later. It consists of three regions of semiconductor material, and we have two types. We have a PNP or an NPN. We're showing an NPN configuration down here in the bottom right, and the schematic symbol above it, and you see the arrow on the emitter of which way the conventional current is flowing. So it comes in the collector, it goes out the emitter. The base, or B, is the controlling element. So applying a current on the base relative to the emitter, it's also relative to the collector, but normally we think of it as the base emitter current. And a very small amount of current on that base emitter junction will cause a much greater current flow through the collector emitter. And that gets more into quantum physics and stuff, which you don't need to know yet. So I said the p-type material has a positive net charge and the n-type has a negative net charge. So we've got charge on either side of the junction, and we cause those to recombine, and that's part of the current flow effect. The three electrodes are called emitter, base, and collector. We usually show them as E, B, and C. And like I said, there's two types, PNP and NPN. And it's just the order of the layers. Field effect transistors use voltage as a controlling element. There's still three layers. They're oriented differently. You'll still have a PNP or an NPN configuration. And then you have some other sub enhancement mode and depletion mode, and that's not on the test. The three electrodes are called gate, drain, and source. The gate is the controlling element. It's the gateway, equivalent to the base of a junction transistor. The drain is equivalent to the emitter, or excuse me, the collector, and the source is equivalent to the emitter. And because these came later, they went, instead of conventional current source, they went to electron flow. So the electrons are coming in the source and going out the drain. So it's different than conventional current, just to confuse people. They could have been consistently wrong, and it would have been easier. The schematic down here is how we represent one of the types of field effect transistors. This would be a junction FET. And we have either a P-type, a PNP type, or an NPN type, depending on the direction of the arrow. They're physically made by having a P-type silicon material with some N-type separated. And then in this case, it's, I guess it's actually a MOSFET, a metallic oxide. There's this oxide layer in here, and there's no current flow. It uses the electric field that's created, because it's kind of acting like a capacitor, to control the amount of current that can flow from source and drain. It's called a pinch effect. And depending on the type, either increasing or decreasing the voltage kind of squeezes the channel and controls how much current can flow. It's kind of hard to show on a simple thing, but it acts like a gate function, and you open and close the gate basically. So which of these components can be used as an electronic switch?
Transistor.
Yeah, we haven't talked about varistors. That's a voltage controlled resistor. We hadn't talked, yeah, we did talk about potentiometers, which is manually controlled resistor. And a thermistor we didn't talk about, and we won't, which is a temperature controlled resistance. It's how you one of the ways to measure temperature. The resistance varies depending on the temperature, and that's what you sense. What is the term that describes a device's ability to amplify a signal?
Alpha gain.
The forward resistance is nothing to do with gain or amplifiers. Likewise, the voltage drop. And the on resistance is just the minimal amount of resistance in the circuit intrinsic to the transistor itself. So it's always there. So when the transistor is fully conducting, it's going to have some minimal amount of resistance, which is what we call the on resistance. Which of the following can provide power gain? A transistor?
Transform.
That's right. A transformer transforms power in equals power out.
Right.
Okay, it can increase the voltage, it can decrease the voltage, or increase or decrease the current, but the product of the two, the power in will equal the power out. So there's no gain. In fact, in the real world, power out is slightly less than power in. A reactor, I assume they're talking about a nuclear reactor.
That's true.
And it converts energy to heat. It's an active device. But I don't know that you call that power gain. It's just
No.
conversion of energy. Same amount of energy you started with, you're just converting it to heat. And a resistor is another transformer, okay? It transforms energy into heat. So it consumes power, but the energy is still in the universe is still the same. Okay, it's just that you change some of it from electrical energy to heat in the resistor. And you also change the amount of current and the potential. So everything is still equal in the world. Which of the following components can consist of three regions of semiconductor material? Alternators are in cars and they just convert mechanical to electrical. A triode, unfortunately, is not a semiconductor, but a triode works the same way as the transistor. And a pentagrid converter, I had to look that one up. It's a special tube, it's two tubes in one.
Oh, Pentagon.
A pentagrid converter.
Never-
And it used to make a single tube radio out of it because it had a diode and a, what was it? Or is it a triode and a pentode in it? It's weird. Anyway, it had nothing to do with a transistor. What are the names of the electrodes of a bipolar junction transistor?
B boy.
Bravo. No, I didn't put any. Some of the, I mean, those other ones are just not even close. What does the abbreviation FET stand for?
Field effect transistor.
D delta.
Okay. I don't know what a frequency emission transmitter is, or a fast electron transistor, or a free electron transmitter. They just made those up. What type of transistor has a gate, drain, and source?
Field effect.
All right. And like we said, a varistor is not a transistor, it's a variable, voltage variable resistor. Do you know what the Tesla effect is?
No,
I don't either. Tesla's a way of measuring magnetic fields. They measure them in Teslas. And the bipolar junction has a base collector and emitter. So it's a part of a bipolar transistor, not a field effect.
that's what I think I thought it was electrical fields.
No, I know,
Well, no, I don't know if it's, but it sounds like it should be.
because trying to remember. Because Walter, the videos I've been watching, he keeps converting between Gauss and Teslas.
Yeah. Okay.
It's a straight version. Okay, so what we learned, diodes conduct in one direction, even if it's a tube diode. They have semiconductor diodes have a forward bias voltage of 0.3 for germanium, 0.7 for silicon. It has an anode and a cathode. The cathode is striped. If it's a light emitting diode, it emits light when it's forward biased or has forward current flowing through it. In other words, it's got to be over that junction. In the case of a light emitting diode, normally they're much higher forward bias voltages, can be 2 or 3 volts. Transistors have power gain, can be used as a switch or an amplifier. The bipolar junction transistor has a base collector and emitter, and NPN and PNP regions, and the field effect transistor has a gate, drain, and source.